Okay, ladies and gentlemen, let's continue with chapter 11, which is on heat exchangers. Let me see if I can change this thing a bit. Okay, chapter 11 on heat exchangers. With the previous lecture, we've looked at the different types of heat exchangers, paragraph 11.1. It was just a general overview of the most important types of heat exchangers that you can expect in industry. And today we're going to continue with paragraph 11.2, which is the overall heat transfer coefficient. And after that, I believe with the next lecture, we will start with paragraph 11.3, the analysis of heat exchangers, after which we're going to look at the log-mean temperature difference method, and then followed by the effectiveness NTU method. And then lastly, paragraph 11.6, the selection of heat exchangers. Okay, so let's continue with paragraph 11.2, the overall heat transfer coefficient. HTC, heat transfer coefficient, paragraph 11.2 in the textbook of Sengel and Gajar. Okay, now in a heat exchanger, let's look at the wall of a heat exchanger. Let me see if I can change this thing a little bit. Okay, this is the temperature on this axis in terms of a heat exchanger, where we're going to assume that on this side we've got the hot fluid and on this side the cold fluid. And let's suppose the hot fluid is at a temperature Ti. The temperature Ti, and then we follow the temperature gradient through the heat exchanger wall. Now in this example, the heat exchanger is that of a tube, but it might also be a plain wall. So the principle is exactly the same. So if that is the inlet temperature of the fluid, or the temperature on the inside of this heat exchanger, then the temperature gradient would look something like that. That would be the temperature on the inside of the inner wall. Then there will be a temperature gradient through the wall, and that temperature would be T outside of the inner tube. And then on this side, the temperature gradient might look something like that. So the temperature gradient would decrease, then through the wall, and then it would decrease again. So here are the temperature differences on this scale. We can transfer it to that scale. But in principle, we've already done it, and we've said that all these changes in temperatures can be presented as different resistance terms. And the different resistance terms would be the resistance of the heat transfer through the inner fluid. Okay. Then it would be the resistance through the wall, and then it would be the resistance through the outer fluid. Okay. This temperature would be Ti, that one there, and that one would be T0. This temperature here would be the inner temperature of the inner wall, and that is going to be the temperature on the outside of the inner wall. And our three resistance terms would be the inner resistance, the wall resistance, and the resistance of the outside fluid. We've done this many times. Okay. Where the resistance of the wall is equal to the ln of the diameter ratio divided by 2 pi KL, if that would be the wall, and that would be the inner diameter, and that would be the outer diameter. Okay. Or it can be equal to x divided by Ka for a plain wall where this is the dimension x. Okay, and that would be the surface area A. Okay. Take note, in the textbook, typically they use L here and an L there, and while this L would be the length in that dimension. Okay, and that is the reason why I didn't use an L here, but rather an X, so that you do not confuse the two L's with each other. Okay, so this is for a tube, and that is for a plain wall. And the resistance on the inside would be 1 divided by the heat transfer coefficient on the inside multiplied by the area on the inside, while the resistance on the outside is equal to 1 divided by the heat transfer on the outside multiplied by the area on the outside. Okay, let's suppose we work with a tube specifically. Let's suppose we work with a tube specifically. Then we can say the area on the inside would be equal to pi multiplied by the diameter multiplied by the length. That would be the surface area for the heat transfer. And on the outside, it would be equal to pi multiplied by the outer diameter. Pi multiplied by the diameter, the outer diameter multiplied by L. Okay, and we've already done it with conduction heat transfer, in the sense that we say we can calculate the heat transfer rate as equal to the delta T multiplied by the total resistance, or total. And we can also write it as U multiplied by the area multiplied by delta T. Okay, different formats. Thus, 1 divided by the total area is equal to U multiplied by the surface area. And this U, as we know, is known as the overall heat transfer coefficient. And its units is watts per square meter, degrees Celsius, or watts per square meter, Kelvin. Whichever you want to use it, whichever one you want to use. So if we look at this equation, we can say 1 divided by U multiplied by the surface area is equal to 1, and I'm going to make this clear to you a little bit more specific with examples. We can say that this surface area, we choose the surface area on the inside. But if we do that, you're going to see that the overall heat transfer coefficient that you calculate is not going to be the same value if you use the area on the outside. So this is very important. It's also equal to 1 divided by the overall heat transfer coefficient on the outside multiplied by the surface on the outside is equal to the total resistance, where this total resistance is equal to 1 divided by this resistance term, the first one, which is 1 divided by the heat transfer coefficient multiplied by the area, plus the resistance of the wall, and it can be either this resistance for a tube, which would then be the ln of the diameter ratio divided by 2 pi KL, or it would be for a plain wall x divided by Ka, plus 1 divided by the heat transfer coefficient on the outside multiplied by the area on the outside. Okay. So note that the product of the overall heat transfer coefficient multiplied by the area is equal to the overall heat transfer coefficient on the outside multiplied by the area on the outside. So, in general, this overall heat transfer coefficient on the inside is not equal to that one. So, the overall heat transfer coefficient on the inside is not equal to the overall heat transfer coefficient on the outside unless, very special case, unless the two areas are the same. So if the two areas are the same, for example, for the plain wall case where we have a plate heat exchanger, then the overall heat transfer coefficient based on the inside area would be equal to the overall heat transfer coefficient based on the outside area. When will that also be the case? When will that be true for this type of heat exchanger? That would be true if the wall is very, very thin. If the wall is very, very thin, then the area on the inside would be very close to the area on the outside. Then the heat transfer coefficients, overall heat transfer coefficients, would be the same. Okay, so U in general is meaningless unless the area is defined. Okay, and what I mean with the area being defined is I must be clear if it's the inner area or the outside area. Especially if one side is finned. Okay, with the previous lecture, I hope you remember, I told you that normally when we've got a gas, if we've got a heat exchanger and one of the two fluid streams is a gas, then normally on the gas side we will always have fins. Okay, so especially if we have fins, then this area on the outside or the finned area is going to be much larger than the other area. And then the two heat transfer coefficients is going to differ dramatically, or they can differ dramatically, and I'm going to show you an example in that regard. Okay. Now, there's another if. Okay. And this if is that if the wall thickness is small. Okay. Now let's look at the wall thickness. If the wall thickness is small for the first case where we have a tube, if we have a tube, then the resistance of the wall would be the ln of the two diameter divided by 2 pi kl, or it will be equal to x divided by Ka. Okay. If the wall thickness is small, then these two diameters are approximately the same. Do you agree? And therefore, this ratio is going to be approximately 1. Okay, and the ln of 1 is 0. Okay. So normally, if the wall thickness is very small, then this term is very, very small, and the resistance of the wall is negligible. And this, in this case, the same. If x is small, then this resistance is also very, very small. Okay. Then there are other cases where where K, so that is the first condition. First condition is when the wall thickness is small. The second condition is when K is large. Okay. Typically, if you use copper, thermal conductivity is in the order of about 300, very, very high. So here we can see that we divide by K. And if K is very high, again, then the resistance is very small. If K is large, then the resistance of the wall in both cases would be very small. Okay, now in many heat exchangers in industry, we use a tube, and you've seen many examples of that with the previous lecture, and in many cases these tubes are made from copper, and the wall thickness also is very, very thin. You do not need a very thick wall in any case. Okay. So the wall thickness is thin, thermal conductivity is high, and therefore the resistance of the wall is negligible. It's very interesting that with many heat exchangers these days you actually get plastic heat exchangers in the radiators of cars. Okay. And again, if you would now look at the resistance of the wall, plastic do not have a high thermal conductivity. But the plastic walls can be made very, very thin. So although this is not high, this is very small, and in many of those cases also the resistance of the wall is negligible. So the heat exchanger is not going to be a better heat exchanger if you change it from plastic to copper. Okay, it's still going to operate very, very well because the wall thicknesses are so thin. Okay, so for this very, very special case, okay, if the wall thickness is small, K is large, and when the inside area is equal to the outside area, okay, if we look at this formula here, if this area is equal to that area, is equal to that area, is equal to that area, and that term is equal to 0, then we can say 1 divided by U is equal to 1 divided by the heat transfer coefficient on the inside plus 1 divided by the heat transfer coefficient on the outside. And that's a formula in your textbook, and many students in the test and exam do a problem and then they start with this equation, which is not a good idea. Okay, so the use of that equation is a judgment call. Okay, use your judgment before you use that equation. In many cases it is not valid. But there are also many problems where you can make your calculations much more simpler and quicker if you do that. And we will do typical examples like that. Okay, now further, take note. Further. Let's look at the case where we've got heat transfer over a wall. And we do not know the relative size of the three resistance terms. Okay. But you are given that the heat transfer coefficient on the inside is 3, the heat transfer coefficient on the outside is 100 or 1,000. Okay. And the wall is thin, thermal conductivity is high. Okay, wall is thin and thermal conductivity is high. Okay. So based on this, the fact that it is thin and K is high, we can say that most probably that resistance is going to be negligible. Okay. If this heat transfer coefficient is equal to 3, then this resistance is going to be 1 divided by 3 times the area on the inside. And this one on the outside is going to be 1 divided by 1,000 divided by the area on the outside. Okay. Now if the area on the inside is approximately equal to the area on the outside, then those two terms are not going to play a role. Okay. And therefore, if we now look at this, and we look at these values, and we try to get a better understanding of what is happening here, we should actually redraw this. And we should redraw it showing that we've got a very high resistance here. This resistance is negligible. Okay. And this resistance is smaller than that one because it's 1,000. 1 divided by 1,000 is much smaller than 1 divided by 3. Okay? So when you work with heat exchangers, you need to think about these things. It is not just calculations. You must try to understand where the resistance is and where the problem is in terms of the bottleneck is in terms of the heat transfer. So we can see that if we want to transfer more heat, we actually need to decrease this resistance on the inside. Okay. Putting fins here on the outside is not going to help us. We must work on the inside. Okay. So if we now look for this at this specific problem, and we look at this and we can see it is valid, the resistance, the wall resistance is small, K is large, the areas are the same, then we can say 1 divided by the overall heat transfer coefficient is equal to 1 divided by the heat transfer coefficient on the outside plus 1 divided by the heat transfer coefficient, the heat transfer on the inside plus 1 divided by the heat transfer coefficient on the outside. That would be equal to 1 divided by 3 plus 1 divided by 1,000. And the result is, if we calculate the overall heat transfer coefficient, it is equal to 2.99 watts per square meter degrees Celsius. What does it mean? It means that the overall heat transfer coefficient, Samantha, the overall heat transfer coefficient is approximately equal to the smallest resistance term, the smallest heat transfer coefficient. Okay. So if you've looked at this problem, you could have guessed the overall heat transfer coefficient is going to be 3. You see? Okay. Let's do the opposite. Let's look at a case where the heat transfer coefficient on the inside is equal to 5,000 and the heat transfer coefficient on the outside is equal to 10. Okay. When you see a 5,000 in comparison with 10, it means that this term, the resistance of this term, is very, very small, isn't it? Because it's 1 divided by 5,000. This resistance is also very, very small. This one is the smallest of all of them, so all the resistance for heat transfer lies in that element, on that side. So if, again, we go and calculate 1 divided by U, it's going to be 1 divided by 5,000 plus 1 divided by 10. What should we guess is going to be the overall heat transfer coefficient? It's going to be approximately 10. Okay. So if you go and calculate it, then the overall heat transfer coefficient is equal to 9.98 watts per square meter Kelvin or degrees Celsius. Okay, does that make sense? Right. Now, typically, when you've got this problem in industry, you would say, but I remember something about fins. So let me solve this problem by putting on fins. Okay, now if you do that, then you've done it already that you can say the surface would be the area of the fins plus the area of the unfinned area. Okay, all the area of the fins plus the unfinned area. So this is for fins. Okay, and if I draw it in terms of color, okay, if I draw it in terms of color, that is my fin, that is the next fin, etc. Then the area of the fin is obviously going to be that area, that surface area there, okay, plus the next one, etc. Which means it would be the area of one fin multiplied by the number of fins, isn't it? Okay, so that is my finned area, that one there, and all the other areas here in between, the areas here in between is going to be the unfinned areas, and I need to add all of them together. But you might also remember that there's something like a fin efficiency. Okay. And taking the fin efficiency into consideration would be saying the surface area is equal to the fin efficiency multiplied by the area of the fin plus the area, the unfinned area. Now, we do not have time to go and revise all the fin theory, but just one or two things that I want to mention. The first one is that, remember, if the fins are short, if it's a short fin, then the efficiency would typically be 1, if it's a short fin. Or if it's an isothermal fin. If it's an isothermal one, then it is equal to 1. And in other applications, it might be, let me just clean the board here. Okay. Other applications would be where we've got a tube, and this is another tube, and we've got the fins connecting all the tubes. Okay. Now for that case, if we look at the center line, the temperature here would be approximately equal to the temperature there, especially if the temperatures in the tubes are the same, which happens in condensation or evaporation. So therefore, those fins would be adiabatic fins. Adiabatic, the tip of the fins, and there's also some formulas that you can use to calculate then the fin efficiency. Okay. We are not going to give much attention in this chapter on calculating the fin efficiency. You've done it in chapter 3. You can go and do it there. Okay. Something else that is important with heat exchangers is fouling. Fouling. Okay. Fouling of heat exchangers is a very problematic thing, and there are two types of fouling. The one is from a liquid on a surface, and I think many of you have seen it in kettles when you boil water for a long time. If you increase the temperature, then there's a calcium layer on the inside. And in some part of the country, it is more severe than in other parts. For example, if the water is very hot, okay, typically in the Western Transvaal areas, there it is quite a big problem in kettles and also in geysers on the inside. With time, the scale becomes thicker and thicker and thicker. Then, the other type of problem that we have is with finned heat exchangers. Typically on the outside of buildings, we've got condensers or evaporators with fins. Okay. And the wind blows, and what happens when the wind blows? You get a leaf that would get in between the fins, you would start getting dust, and then it would rain a little bit and everything stays there, and then there's a little bit more wind, etc. And with time, and there's also pollution, there will also be a buildup of scale or fouling on the outside of the heat transfer area. And we need to take that into consideration when we design heat exchangers. And we do that by making it very simple, by just adding two resistance terms here. If this is the wall, we put a resistance term on this side and another resistance term on that side. So the result is that we would say that 1 divided by the overall heat transfer coefficient multiplied by the surface area is equal to 1 multiplied by the overall heat transfer coefficient on the inside, the area on the inside, is equal to 1 divided by the overall heat transfer coefficient area on the outside, is equal to the total resistance. And the total resistance is then going to be 1 divided by the heat transfer coefficient on the inside multiplied by the area on the inside, plus the fouling resistance on the inside multiplied by the area on the inside. Okay. So if this is our wall, okay, and that is the fouling on this side, we would say that that resistance is equal to RFI divided by the area on the inside, plus the resistance of the wall, plus then the fouling on the outside of the surface multiplied by the area on the outside, plus 1 divided by the heat transfer coefficient on the outside multiplied by the area on the outside. So again, we've got another fouling there. So if we look at the total resistance, then we would say it is equal to that resistance there, okay, which is equal to the resistance on the inside, which is equal to 1 divided by the heat transfer coefficient on the inside multiplied by the area on the inside, plus the fouling resistance, okay, that resistance there, then the wall resistance, the resistance of the wall, okay, then again the resistance of the fouling on the outside, the fouling resistance on the outside, plus the resistance of the fluid on the outside, which is 1 divided by the heat transfer coefficient on the outside multiplied by the area on the outside. Okay, so there are all our resistance terms. The resistance of the fluid on the inside, the fouling here on the inside, the wall resistance, the fouling on the outside, plus the resistance of the flow on the outside. Those are all our terms. So we have made it very, very simple to handle. Now, unfortunately, getting these fouling values or predicting them is very, very difficult. A lot of research has been done, and it's very difficult research. A few years ago, I was involved in a project where we had a very, very simple experimental setup. The experimental setup was just a tube which was being heated. And we had some of the municipality water flowing through it, like over a period of a year. And then we could determine this resistance by very, very accurately measuring the mass flow rate. So as the resistance increases, the mass flow rate must obviously decrease. And it was a nightmare trying to understand what is happening. Because if you look at the water, take water samples every day, then in water, I think it's the most complex fluid that there is to work with. Because inside it there are, 50 different things. There's iron, calcium. You can't believe it's the pH. You can't believe what is in water. And I've given up because we just couldn't make sense of the results. So therefore, trying to predict what the fouling is going to be is very, very difficult. I think it's sort of an art, predicting it. But just to give you an indication, in table 11.2 in your textbook, okay, in table 11.2, typical fouling value, just order of magnitudes for air would be, and the units for fouling would be square meter, Kelvin per watt. Typical values for air would be 0.0004. Okay. And for water, if the temperature is lower than 50 degrees Celsius, then it would actually be very low, 0001. Okay. But the moment that the temperature increases to higher than 50, then it would increase to approximately 0.0002. So what is interesting is that the fouling of air is actually larger than that of water. You see, it's not what we would expect. We can also see that the fouling increases significantly if the temperature increases to temperatures higher than 50 degrees Celsius. Most geysers, hot water storage tanks in our houses, thermostats are usually set to temperatures of 60, 65 degrees, something like that. If you set it to 50 degrees and lower, then the fouling would of course be much less. Okay, let's start with an example. The example is based on example 11.1 in your textbook, but I've made a few changes. And the example looks like this. Okay, we have hot oil. We've got a tube-in-tube heat exchanger. Tube-in-tube heat exchanger. And here we've got cold water. And obviously cold is a relative value, and the mass flow rate of the cold water is 0.5 kilograms per second. And here we've got hot oil at the temperature of the mass flow rate of 0.8 kilograms per second. The diameter of this inner tube is 20 millimeters, and the diameter of the inner annulus is 30 millimeters. Okay. And it's thin tubes, and with that we mean that the inner diameter is 20 and the outer diameter is also 20 for all practical purposes. And the question is to determine the overall heat transfer coefficient. What is not given is the inlet and outlet temperatures. We will get to that later. But what is given is the average temperature of the oil and the average temperature of the water. Okay. And those are, the average temperature for the oil is 80 degrees Celsius, and the average temperature for the water is 45 degrees Celsius. And in table A13, we can get the values for oil, and in table A9, A1 or A9, I can't remember, you can get the values for water. Now, the density for water is equal to 852 kilograms per cubic meters. The Prandtl number is equal to 0.138, and the kinematic viscosity, which is the dynamic viscosity divided by the density, is equal to 3.794 multiplied by 10 to the minus 5 square meters per second. And the same values, the density, the Prandtl number, and the viscosity for the oil is 990.1. Prandtl number is 3.91, and the viscosity is 0.602 multiplied by 10 to the minus 6. Okay, since we've got this two columns, I would recommend that you use the two columns in the problem that we're going to work out now. So on the right hand side we're going to do the calculations for the water, and on the left hand side we're going to do the calculations for the oil. Okay, so that is the oil side and that is the water side. Okay, let's start with the water. Yep.
The Prandtl number for the oil, I think you've used the K value instead of the Prandtl.
Oh, okay, just check that for me. Oh, wait, no. I think the K value for the water is 0.138 watts per meter Kelvin. And the K value here for oil is 0.637. Is that correct?
Sorry, so which one's oil, which one's water? Could you kind of mix it up?
This one is for water.
You say oil from the top.
Sorry?
But you say oil.
Where did I say oil? Okay, we are out of time in any case. I will look at it and then we will continue with the problem with the next class. Thank you very much.